So Vt equals r omega. And let's keep in mind we're talking about something rotating around. Now Vt, that's the distance traveled over time. Let's imagine that our point, for some smaller time, not one complete period, let's imagine that our point actually rotates through some arc length, we'll call it delta s. So let's imagine just part of one motion, part of one complete circle, not the whole thing, but just part of it. So let's imagine that this takes some amount of time, delta t. So the tangential velocity we can think of as the distance over time, delta s over delta t. And this equals r times omega. Well, let's imagine that during this time, the point has rotated through an angular displacement of delta theta. So omega, which is the angular displacement over time, we can write as delta theta over delta t. And then multiplying both sides by delta t, we have delta s equals r delta theta. Or if we wanted to look over some larger macroscopic time for some larger arc length s, we can say that s equals r theta. So we have a very, very simple relationship between the angle and the arc length. The arc length is just r times the angular displacement, or whatever the angle is, theta. So we can imagine s may be measured from the x-axis like that, and theta is then whatever that final angle is measured from the x-axis. So we've got s is equal to r theta. Very, very simple relationship. We also know that for anything going around in a circle, we know that we have a centripetal acceleration. And we know from our analysis of uniform circular motion, the centripetal acceleration was equal to v squared over r, where v is what we've been calling the tangential velocity. Well, if v is equal to r omega, we can write this as r omega squared, there's the linear velocity, divided by r, or r squared omega squared over r, or the centripetal acceleration is, one of the r's cancel, r omega squared. So we have a very simple relationship for the centripetal acceleration in terms of the angular velocity and the radius of the point in question. So remember, the radius r is whatever the distance is from the axis of rotation to our reference point. Now, what if omega is changing? If omega is changing, we know we also have the velocity is changing, which means we have a linear acceleration as well. So this is an acceleration, the centripetal acceleration, that we have even if the speed of the motion is constant. However, if the speed of the motion is changing, in other words, if we have an angular acceleration, we must likewise have a linear acceleration. So the linear acceleration at that point must also be changing. In other words, the tangential speed must be changing. Well, how much is that changing? Well, let's think about the tangential acceleration. In the same way that we looked at other accelerations, we can imagine that over a small time interval, what is happening to the tangential speed? Well, I'll work through this kind of completely, although we don't need to keep all this in mind. Let's remember this will then be the limit over a small time interval of the change in the tangential speed, which would be the final tangential speed minus the initial tangential speed over delta t. And then this is going to be the limit of the final tangential speed. There's someone at the door making faces over there. The final tangential speed we can find from the final angular speed. Remember, the tangential speed was r omega. So this will be r times the final angular speed minus the initial tangential speed, which will be minus r omega naught, using the initial angular velocity, over delta t, which we can write, limit delta t goes to 0 of, I'm going to factor out an r here, factor out an r, and we get omega minus omega naught over delta t. Now, r is a constant value. We're going to assume that the reference point is not moving closer or farther from the axis of rotation, so r is a constant value. So I'm going to pull that right out from the limit. I'm going to pull it out front, so we can write this then as r times the limit as delta t goes to 0 of omega minus omega naught over delta t, which we can write as r times the limit of delta t goes to 0 of omega minus omega naught. Well, what's that? What's omega minus omega naught? That is delta omega over delta t. And what is delta omega over delta t? That's the average angular acceleration. And what is the limit of that as delta t goes to 0? It is the instantaneous angular acceleration. So this is all equal to r alpha. So that was a great big derivation to give us the final result that at equals r alpha. So what do we have? We've got some very, very simple results. We have that the arc length is equal to r times theta. Let's keep in mind what's going on here. This thing is rotating, our reference point is moving around. The distance traveled, s, is equal to r times the angular change theta. So s equals r theta. The speed, the tangential speed, is equal to r omega. Or, using the term that we did before, just v. v equals r omega. A equals, A equals r alpha. But let's be a little bit careful. This is the tangential acceleration of it going around. While at the same time, we have a centripetal acceleration, which is r omega squared. So we've got some very, very simple relationships between the linear quantities for the motion and the angular quantities for the motion. Some very, very simple results. Now, there's one more type of motion related to this angular motion that I want to talk about. One very specific type of rotational motion, and that is a combination between rotational motion and translational motion. Something that is rotating and translating at the same time. Okay, so here I've got a wheel, and we're going to imagine the wheel is rotating, but at the same time, the wheel is going to be translating sideways like this. So rolling, rotating, and translating. Now, there's a particular relationship between the rotational motion and the translational motion that I want to look at. Let's imagine that this is actually maybe a tire, a wheel on a car or a bicycle or something like that. We might have the tire rotating very rapidly while translating more slowly, so that it's kind of skidding along on the ground. This might be what would happen if you're in a car and you give it a lot of gas, the tires start spinning, but the car hasn't started translating rapidly enough. So this would be where the rotational motion was faster than the translational motion. Another extreme might be if the tire was moving more slowly, but was translating more rapidly, so that it's kind of skidding along this way. Now, this would be what would happen if you're driving along, you slam on the brakes, the tires stop rotating, they're not rotating very much, but the car is still moving along. So you'd be skidding along if you jammed on the brakes. Again, the tire is sliding along on the ground. Now, in between those two extremes, we have a situation where the tire is rotating at just the right speed for the translational motion so that it remains in contact with the ground the whole time. At no point is it skidding or sliding. It's remaining in contact with the ground the entire time, never sliding. This type of motion is called rolling without slipping. And that's the motion I want to talk about, when the rotational motion is just right for the translational motion, that the tire or the rotating object remains in contact with whatever it's rolling against. Okay, back to the board. All right, so what we're going to do is we're going to look at rolling without slipping. Now, let's draw a picture here. Let's say here's the ground, and I'm going to draw our wheel, let's say over here, in contact with the ground. And let's imagine that this wheel rotates along, and at some later point, it's over here. Okay, so here's the tire, rotates along, and then here it is initially, here it is finally. Now I want to draw in some points here. Let's draw a point, a reference point on the wheel where the wheel is in contact with the ground initially. I'm going to call that point A. Here's the center, and we'll assume the wheel has some radius r. Now, this wheel rotates along. Now, what happens to A? What happens to the point A? As the wheel rotates around, A rotates up and comes up, and is going to be up at some point up here once the wheel is rotated along. So A is now up here. Now, another point I want to talk about is this point where the tire is in contact with the ground in the final position. We're going to call that point B. Well, where was B back here? Imagine back here, B would be up some point up here. So there's B. So A in contact here, the tire rolls over, A has now rotated up here, B rotating down to contact with the ground there. Now let's imagine that during this time, the wheel has rotated through an angle of theta. So that angle there is theta. So as it rotates around, the wheel is rotated through an angle theta. Now let's imagine that this distance here is the distance that the wheel translates. Now how far is that? Well, if the wheel remains in contact with the ground the entire time, if it rolls without slipping, and this is the important point, this distance that the wheel has rotated is going to be the same as the arc length along that wheel there. So this distance must be the same as that distance if the wheel has rolled without slipping. Does that make sense? That's the important point here. So this arc length that I'll call S must be the same as this distance here, S, that the wheel has moved horizontally. Does that make sense? Any questions? No questions? All right, good. Let's move on. Okay, let's imagine that this whole motion takes some time, delta t. Now, what do we have? Well, we know that the angular velocity of the wheel is going to be the angle through which it rotates over the time. In this case, well, let's just, to be consistent with what we did before, let's call this delta theta. I'll call that delta theta. Omega is going to be equal to delta theta over delta t. So that's the angular velocity. Delta theta over delta t. Now, how fast is this wheel moving? How fast in a translational direction is it moving? V. Well, it's going to be the distance traveled over the time. Well, how far has it traveled? It's traveled a distance s. So we know V is equal to S over delta t. Okay? Now, one more thing. What do we know? S is the arc length. And the arc length we know is related to the angle using the radius, r. So we know that s is equal to r delta theta. So I'm going to write this here. S is equal to r delta theta divided by delta t. Well, look at that. What do we have? We have that v is equal to r delta theta over delta t is omega. V equals r omega. Now, you might say, well, we already did that. We got v equals r omega previously. But let's keep in mind, those are actually two different things. That v that we were talking about before was the translational velocity of a point on the edge of the wheel. While in this case, this v is how fast is this wheel moving horizontally? How fast is it translating? What we now have is that in order for an object to roll without slipping, its translational velocity has to be the same as the tangential velocity of a point on the edge of the wheel. So in order for this to roll without slipping, we have to have the translational, the velocity of the wheel moving translationally has to be the same as the tangential velocity of a point on the edge of the wheel. That is a very, very different result than what we had before. So let's stick some numbers in here. Let's imagine we have a car. Okay, so here's our car. Okay, and our car is driving along. And let's imagine that it starts from rest. And over 15 seconds, it accelerates with a linear acceleration of 0.750 meters per second squared. The radius of a tire is 0.335 meters. The question is, how many radians, to what angle does one tire rotate during this time? Okay, so let's think about this. The car is starting from rest. It's starting to speed up. The tires, starting from rest, start to rotate. The car is accelerating linearly at 0.750 meters per second squared. The tires have a radius of 0.335 meters. The question is then, through what angle do the tires rotate in this time, 15 seconds? So we are relating translational quantities with rotational quantities. And we're going to assume, we have to assume to answer this, that the tires are going to roll without slipping. Well, if they're rolling without slipping, we know then that we have that relationship that the translational velocity must equal r times the angular velocity. Okay, so let's think about this. We're saying that it starts from rest, so we know that the initial velocity is 0. Likewise, the initial angular velocity for the tires is also 0. What about, we know if we've got a linear acceleration, then we know we must have an angular acceleration. So what is the angular acceleration? Well, we know that a is equal to r alpha, so alpha is a over r. So alpha is a over r. In other words, 0.750 meters per second squared divided by r, 0.335 meters. Divide that out, and what do we have? We have that alpha is 2.24 radians per second squared. So the tire is going to rotate, speeding up at 2.24 radians per second squared. Well, going to the kinematic equations, the rotational kinematic equations, we can think about what equation can we use. Well, let's put down the variables. We've got theta naught, theta, omega naught, omega, alpha, t. Again, in general, we can set the initial angular position equal to 0. What is theta? Well, theta, that's what we're looking for. Omega naught, well, we know we're starting from rest, so omega naught is equal to 0. Omega, well, we haven't calculated that, so we don't know that at the moment. Alpha, well, we did figure out that. We got alpha from the linear acceleration, so we know alpha is 2.24 radians per second squared. T, well, we know that this takes 15 seconds. So, is there an equation that we can use to figure out theta? Well, yeah, actually, it's the third one. So we've got theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared. Theta naught we know is 0. Omega naught we know is 0. So what do we have? 1/2 times alpha, 2.24 radians per second squared, times t, 15 seconds squared. Multiply that out, and what do we get? We get theta is equal to 252 radians. There we go. Very straightforward. In this case, we've got a problem that's mixing the linear and the rotational motion. We could have solved this actually if we had solved the linear part first, knowing the initial velocity, the time, and the acceleration. We could have used this to find the distance traveled, and then knowing the relationship between the distance and the angle, we could have solved it that way. This way we solved for alpha and then used the angular equations to solve for it. Why don't you try and actually do it the other way? See if you can find what is x, the distance, and then using the distance traveled is r theta, solve for theta that way and see if you get the same thing. And you should get the same thing. Alright, one more quick point. Are these rotational quantities, are they vectors or are they scalars? Well, you might think about it. How do we describe rotational motion? If we were to look at this wheel again, okay, is this motion the same as this motion? Well, no, those are different rotations, but you could say one's positive, one's negative. We don't need a vector for that. But is this rotation the same as this rotation? Okay, well, definitely not. Those are very, very different rotations. So perhaps we do need some kind of vectors to describe rotational motion as well as translational motion that we've already looked at. Well, how are we going to define a direction? Let's imagine that we've got this wheel and this wheel is rotating. We've got some angular velocity. How are we going to define an angular velocity direction? How do we define a direction along with that? Well, what we're going to do is use a very, very important idea. Now, I'm sorry about this. Don't blame me. It's not my fault. I didn't come up with it. This rule that we're going to use is called the right hand rule. This was obviously developed by someone who is right-handed. If you are left-handed, I apologize, but don't blame me. Blame whoever came up with this idea. But using your right hand, if you rotate your fingers in the direction of the rotation, like this, your thumb will then point in the direction of the vector associated with that rotation. So in this case, if our wheel is rotating this way, the direction of omega is actually out of the board. Now I'm going to use two new symbols to represent these third dimensions, the third dimension. We've been drawing things in the board, but if we want to talk about things perpendicular to the board, I'm going to use a circle with a dot and a circle with an X to represent directions in and out of the board. Now these are pretty easy to remember. If you think about an arrow, what does an arrow look like? At one end of an arrow you have the point, and at the other end of the arrow you have the feathers or the fletching. Now if you look at an arrow coming toward you, what do you see? You see the point of an arrow. So this is the point of an arrow coming out of the board. While if you look at the back end of the arrow, you see the feathers or the fletching in the back. So this is an arrow pointing away from you, so this is pointing into the board. So I'm going to use this symbol to mean out of the board, this symbol to mean into the board. So with a rotation in this direction, the angular velocity vector will point out of the board. While if this were to rotate in the other direction, say this way, rotate your fingers this way, this velocity would point into the board. Now, what if the wheel were actually rotating, say, this way? Well, in that case, rotate your fingers this way, that velocity would point upwards. Okay? So, that's just a little introduction to the right-hand rule and how it applies to rotational quantities. We'll talk more about that later on as we look at other rotational quantities when we look at rotational dynamics next time. Okay, thanks a lot.